Good day. My name is Brian Kelly. I'm Global Applications Engineering Manager for Honeywell Thermal Solutions, and I want to welcome you to this session to discuss emissions reductions that matter, advances we've seen in combustion technologies. In today's world, furnace OEM builders and end users who want to upgrade their heat treatment processes face a multiple of operational challenges. Not only are they under pressure to optimize performance, reduce cost, minimize waste, but also in many areas meet increasingly stringent NOx emissions regulations and other standards in every market in which they do business. So it can be difficult to focus on these necessities while delivering the process and product quality required for commercial success. So what we want to discuss here is eco-friendly burner technology. So what does that mean? Well, we want lower emissions, we want higher efficiency. Higher efficiency results in lower fuel usage and a lower carbon footprint, which we've heard a lot about in recent years. And related to burner technology is also the control of those burners. So we'll talk a little about control systems as well. So burners, I'm a burner guy. So traditional furnace burners. Generally on most of your heat treat furnaces, you're looking at if they're direct fired high velocity burners. Why do we use high velocity burners? Generally to cause mixing in the furnace vessel itself to promote uniformity. And with those high velocity burners, and I'll show this in the next slide, is a degree of exhaust gas recirculation, internal recirculation within the furnace body itself. But we also have our indirect fired applications that were generally fired into a U tube, a W tube, a Trident tube, generally may have a furnace atmosphere in there that can't take the product's combustion or may be explosive, or the product itself is intolerant of products of combustion. Okay, so on to our subject of direct fired velocity burners. You'll see the burners on the left there, pretty traditional looking burner with a reduced sleeve outlet. Can be a silicon carbide or an alloy for lower temperatures, refractory for much higher temperatures. These are generally fired with ambient combustion air, at least in the US, but certainly are capable of preheated combustion air. Like we discussed, high velocity to achieve temperature uniformity. As the little diagram shows there on the right, the high velocity jet coming out of the burner itself is entraining many more times its volume in what is relatively cool furnace gases. So that tends to cool the burner flame off, which helps to reduce NOx emissions a little bit. And we also have different burner designs that are lower in NOx than maybe some other traditional nozzle mix burners. Now to our indirect fired burners. Generally, we're talking radiant tube type fired furnaces. It can be a W tube, as pictured here, or a simple U tube, what's called a Triton tube. That two burners fire into a central exhaust leg. And these are often fired on ambient combustion air, at least here in the United States, but most burners are capable of preheated air, combustion air, just like the direct fired burners. Traditionally, these burners have been designed to be a long luminous flame to get a better temperature uniformity, so that uniformity then is transferred to the load as well. As we discussed previously, generally these type of indirect fired furnaces have some type of atmosphere to promote the treatment of the steel or the product being heated, or the product itself is not tolerant of the products of combustion for a direct fired situation. So our first slide there was talking about being that eco-friendly burner. So what do we want to do to drive efficiency up to reduce our costs? We can add traditionally recuperation, which takes the exhaust gas out of an open fired furnace or an indirect fired furnace, takes that exhaust gas and preheats the combustion air. That gives us a better overall efficiency and reduces our fuel usage because we're now not having to heat that cold air or that delta T of that cold combustion air. But the consequence is with preheated combustion air, it results in higher flame temperatures, which a higher flame temperature increases your thermal NOx and is going to increase your NOx emissions overall. There's no way of getting around that. Or we'll talk to you about a few little secrets. Maybe we can try to reduce that. So direct fired furnaces and recuperation. There are many multiple burner furnaces that utilize an external recuperator, which is a heat exchanger that's attached to the furnace stack. The hot exhaust gases go through tubes or through plates. That cold combustion air comes in, as you'll see in this simple little diagram here, goes through the heat exchangers, preheated, and then that preheated combustion air is fed to the burners. Again, higher efficiency, but will also, in traditional burners that have not been designed for lower NOx emissions or some type of method to get a lower flame temperature, you will see higher NOx emissions. Alternately, we were talking about the indirect fired recuperation, or in this case, radiant tube burners plus recuperation. Generally, it looks like our plug recuperator there on the left. Pretty simple type of concept here. We install the recuperator to the exhaust leg of this U tube or a W tube. The burner fires. You'll see, looking for that long luminous flame in our traditional radiant tube burner. Those exhaust gases wash over that externally recuperated. We have cold combustion air coming in from the bottom there, going through the tubes. The heat is exchanged, and then that preheated combustion air is fed to the burner. Again, increasing our efficiency, reducing our necessary fuel to get the work done, but increasing the NOx again with that increase in flame temperature. So from our first slide we had there, hey, we want some eco-friendly burner technology. We want it with lower emissions and that higher efficiency to get our fuel usage down, lower that carbon footprint. But everything I've just shown you to get that higher efficiency, reduce that fuel usage, be more friendly to the environment, we're driving up those nitrous oxide emissions, which is not so friendly to the environment. So what do we do? Well, many years ago, people smarter than I am started looking at how do we combine this and try to get some lower emissions while maintaining that higher efficiency. So many of you probably have seen this type of burner. It's called a self-recuperative burner. In this case, it's in the direct fired application we've already talked about with high velocity burners. What you'll see in this case is that the picture on the right is showing that high velocity flame. So in this type of instance, we're maintaining a high velocity. At the same time, it's incorporated with its own recuperator. So as the burner fires, there's an inductor or some type of system to create a vacuum to suck the exhaust gases over the outside of that recuperator to provide our heat exchange to preheat combustion air and maintain the higher efficiency. The higher velocity of the burner helps entrain some of those flue gases to try to lower that peak flame temperature. Now we can look at our self-recuperative burner in an indirect fired application. What you'll see here is both a single-ended radiant tube as well as a P tube on the lower right there. P tube, you can see, sort of mimics a U tube for surface area, so that type of radiation. So the concept here, or the application, is that we now have in the radiant tube, rather than our long luminous flame like in our traditional U or W tubes, we have that high velocity flame shooting a high velocity jet of flame down an inner tube that's protecting the outer tube, but it also provides a direction for the hot gases to go to the end of the tube, recirculate back, and then the exhaust washes over the recuperator, obtaining our heat exchange, preheating that combustion air to get our efficiency up, but that high velocity jet also re-entrains some of that exhaust gas. So what that's doing is working to reduce our emissions as much as possible in this type of burner technology. So we've talked about cold air, hot air with separate recuperators, and now our self-recuperative burners. Let's put some numbers on this, or at least visually take a look at this. So here I've got in my red box here, the top there is a sealed in nozzle mix burner. So that's our cold air burner with an efficiency of about 45%. With that kind of efficiency, that means our furnace temperature will approximate probably about 1800 degrees Fahrenheit or 1000 degrees Celsius. Under those same conditions, that same sealed-in nozzle mix burner with that remote recuperator is going to get you about 60% increase with that preheated air capability. Then in our last one there is our self-recuperative burner, and that design gets us up towards the 70% efficiency mark, which is a pretty good number. It's going to to get us that efficiency gain or that cost reduction. But again, we have to look at our NOx emissions as well. And we'll discuss the design of that self-recuperative burner next. So let's examine the basic design of a self-recuperative burner and its function. So traditionally we have cold combustion air coming in as well as our gas coming into the burner as well. Our combustion air comes and is split into two channels. One has a portion of the air internal to an air gas guide tube and some external. As you'll see, the air is proceeding to the right down the internal of the burner's integral recuperator. On the outside, we have our hot flue gases washing over the recuperator, heating it up. So as the cold air proceeds down in a counterflow direction to the exhaust gas, our air gets preheated as it exits the burner. There's a primary air that's getting mixed with the fuel coming out of the converging burner nozzle, and the other is coming around that nozzle to provide a slightly staged combustion. Depending on the length and diameter of the recuperator, there's different efficiencies that are associated with that. Of course, as we had discussed before, as we preheat the air, our higher efficiency comes into play, but also the NOx gets higher. There's method and designs that have been incorporated to try to minimize that in a standard self-recuperative burner, but over the years, we're seeing our NOx emission standards getting lower and lower, and other methods to further lower NOx have been taken and accomplished. So as these emissions need to get lower and lower, what methods have been taken to further lower the NOx in self-recuperative burners? Many of you may be associated with what's called flameless combustion. It's been coined Flox, Invisiflame, other trademarks in the industry. So in looking at the slide here, what we would call the flame mode of the burner is kind of a standard firing as we just looked at the design of the self-recuperative burner. There's a traditional nozzle that attaches the flame with air and gas mixing on that. Some of the combustion takes place in our burner combustion chamber, and the rest is exiting through the burner. It's a high velocity stream, so as before with the high velocity burners, it's entraining some of the exhaust gas. So it's a high reaction speed right at the inlet exit of the burner, so a high energy density in that flame as well. So there's some intake of the exhaust gas in that flame zone, but it's a relatively high temperature. And as we know, with a higher flame temperature, that's our main driver. NOx is thermal NOx, so it's relatively in relation high levels of NOx formation, even with some of this recirculation of the exhaust gas being entrained into the flame. So flameless combustion. So whether the flameless combustion mode is being entered in either an indirect or direct fired situation, generally that flameless combustion is done at above auto ignition of the fuel, in this case 850 degrees C, 1560 degrees F. Generally we say it's about 1400 degrees F for auto ignition. There's always a safety factor that we need to employ to make sure that we are safe. So as you can see in this mode, we are no longer attaching our flame to our burner nozzle itself or the burner flame holder. We now have a different method of injecting the gas with the air that now is flameless. We no longer have a high energy zone right in front of the burner causing peak flame temperatures. So in this case, with a high volume of gases exiting the nozzle, we have a high intake of exhaust gas into the combustion air. It's a lower reaction speed, so our energy density is lower in the reaction zone, so that in turn lowers our peak flame temperatures in that reaction zone. And with that reduction in flame temperature, we minimize or reduce our formation of NOx in the burner itself or in the application. So for this slide, we're showing a visual representation of these two different modes, both flame and flameless heating. This happens to be in a single-ended radiant tube application, which many of these burners are applied to. So in the case of our upper diagram, you'll see that legitimate or flame front in the burner nozzle with a high velocity jet exiting into our inner firing tube, recirculating around that in our single-ended radiant tube, with some of these exhaust gases being pulled back in to help lower the NOx as much as possible. Conversely, once we get above our switching temperature, we go to our flameless heating mode, in which you'll see there's no flame depicted coming out of the burner. It's just air and fuel. And then because of our temperature, our reaction zone is moved down the tube with a lower flame temperature. We also still have the recirculation around that inner tube on the outside, or an inner diameter of the outer radiant tube, or the single-ended tube, with our exhaust gases still washing over the recuperator, some being entrained maybe to a greater degree into our inner tube design, and effectively having our indirect heating in that method. Burner designers and burner manufacturers continue to innovate, continue to work on designs to lower the emissions levels from self-recuperative burners, among others. What this graph is representing is the latest in low NOx self-recuperative burner emissions. What you'll see represented by the top line, both in red and gray, is your traditional self-recuperative burner with no flameless technology. What you'll see on the left-hand side there is at our auto ignition or 850-degree switching temperature, and some of the latest technologies, the latest techniques to lower NOx with our emissions levels at 60, 80 to 100 kilowatts. These are some of the lowest NOx emissions that we've seen from self-recuperative burners, and are striving to meet what the regulatory agencies are asking for. What this slide depicts is a pretty standard control method for self-recuperative burners. On-off control, pulse-fired. Generally, what that will get you is your maximum efficiency, maximum NOx reduction, and maximum uniformity in your single-ended radiant tube. What you have as basic control components are air and fuel control valves that pulse on and off together, controlled by some type of burner control unit, and generally a pressure switch to confirm flow. What we have in this slide is the layout for our low NOx control option with the low NOx burner. In this case, you'll see multiple gas inlets, as well as with this burner design, multiple air inlets. During our flame mode, in this particular setup, we've got an air control valve that's controlling the air to both a primary and secondary air inlet. And in the mode for a flame operation, our V1 and V2 valves are feeding gas to the 12 o'clock position in the burner, with the secondary gas V3 closed. As we proceed to our 850C temperature to go into flameless, that primary air valve closes along with the V2 gas valve, and then our flameless gas valve opens, with gas entering the center, down the center of the burner, along with the secondary air. It's staging air to go into flameless and achieve those low NOx results that we're looking for. What we're depicting here are just examples of air and gas trains, just to put a visual representation to it and what a package may look like from a burner manufacturer. Generally, our burner suppliers will want to supply a completely packaged burner, because then the technology, the gas and air valves, the cycling required, all are under their control. It's all sized and assured to properly operate on a customer's furnace, and again, achieve the results that that customer is looking for. Someone once said that power is nothing without control. Without the proper valves, without the proper burner controls, without the proper furnace controls, the burner can't do the job it's been designed to do. All-in-one modular burner control solutions are available for these type of multiple burner applications, and are essential to have a positive result from this newer technology. These newer burner control units are updated state-of-the-art designs to meet the requirements of the market and these type of systems. They're generally highly configurable, allow high temperature modes, can have and accommodate both firing modes and flameless operation, have communication capabilities, so Profibus or Profinet or Ethernet IP network communication ability, and generally will have fail-safe measures between those burner control units themselves and the furnace control units. And what this is allows a simplified system design. These type of units are designed to be located at the burner versus being housed in a main cabinet, and they enable better system integration and a lot of decreased installation costs with these type of communication abilities, rather than all the wiring coming back to a main panel. The bus communication allows a daisy-chained wire for communication to control the burner throughout the furnace. It can save tens of thousands of dollars in wiring costs, and enables you to better integrate the system. Now we have our burners, our control valves that are controlling those burners via burner control units and furnace systems that are running that process, that whole furnace. Today, there's solutions that are available that allow you to get connected, that allow you to look into that data that's housed in some of the control units, because some of the assets that we have running these furnaces that may have critical data, critical knowledge of what's going on with that furnace, that can be available in real time and help operators and managers make real-time decisions quickly and efficiently. Today, there's technology and systems that can harness the data that we've got in our devices that are not always visible or hardly visible to operators or managers that need to manage their furnaces. Flame safety devices, temperature controllers, existing equipment, new equipment that are monitoring and controlling our burner systems, our combustion systems, can be enabled to transmit data to a secure cloud location and submit that to both a smart device that may alert you to a burner problem, a flame signal problem, a fuel flow problem. Further under that, that data can be submitted to an asset and process performance model that can provide you with fault analysis and predictive maintenance, analytics, and even allow you to get to root causes, alert you to problems that over time will cause you issues, both with combustion system performance, but performance of your furnaces, your processes, that can eliminate downtime and further enable you to better manage your combustion assets. I want to thank you for taking the time to attend the session today. If you're interested in what we've discussed today, you can please feel free to stop by our booth and see the exciting new technology from Honeywell that's related to what we discussed today. Have a great day.